would see what is the modes of acquiring a sparse signal and whether the sparse signals are really practical or they are available in the real world or not. And the second thing, then we'll move on to why and how this compressed sensing is going to play a role in this acquisition or the measurement of the sparse signal. And the next topic, then the next thing, then we should ask that what are the modes of acquisition, so that can ensure that there is a unique measurement exists for all such sparse signals. Okay, so let's start with what is called a sparse signal. So if we go by the definition English literature, that sparse means we expect things to be less in number. So here we are basically looking at a discrete signal of length 10, and we're only having 3 non-zero entries in this discrete signal, but most of the entries are 0. So such kind of signal, we term it as sparse signal. But what is the criteria? At least if you ask me philosophically, what should be the threshold on the level of non-zero entries that we should define that as a sparse? It is well accepted in the community that whenever a signal is having non-zero entries less than, much less than is always better, but less than at least half of its dimension, we consider it as a sparse signal. But then comes the real world signal. Of course, sparse signals are also real in many occasions. For example, if you consider earthquake, somebody is observing a seismological observation, he doesn't get a signal most of the time. So of course, it's a real life sparse signal, but there are many other examples as well. But at the same time, most of the time, we don't see the signals to be sparse by itself. So something, it appears like this if I'm writing a time domain signal. However, if you go to a basis, we find a proper basis such as DCT for this signal, we can always find its representation which is sparse. So sometimes it's not sparse, but we can find a suitable basis that can make it sparse. So that way, we call this kind of signal as sparse signal, but implicitly sparse signal. So another such real life example, if you see, like practical one, is the images or the imaging problem we deal with day-to-day life. The images are, of course, you can say some images are sparse by itself, for example, X-ray and this MRI and all. But these natural images, by itself, they are not sparse, they're quite dense. But however, throughout the revolution of transforms, people have come up with various interesting orthogonal, non-orthogonal transforms, which can give us actually such interesting coefficients in the transform domain. For example, a wavelet transform here, it has been done on this image. And we could see that clearly that the number of coefficients are quite minimal. So here it's not exactly the arrangement of the position of the coefficient. Here I have plotted in 1D the decreasing order of the coefficient amplitude. Okay. So this is another kind of sparse signal which is not sparse, but of course the tail is quite minimal. So we can say that if you set a threshold at a level of energy, then you will find that most of the coefficients are 0. So now we come to the point CS. So why CS and what is CS and CS versus sampling? First, let's describe this acronym that compressed sensing is well known in the community. Also, some people call it as compressive sampling. So more or less, they mean the same thing. There is no difference. So what does it mean? That it is a kind of sampling procedure that expect to compress the signal in the acquisition process itself. So if we consider sampling, the traditional sampling, so what do we do in conventional sampling? We can term it as a local sampling, or we basically extract, if you consider time domain signal, we extract each time sample locally for a conventional sampling procedure. Be it even image or any 2D signal also, you take a point in the space and extract that point. But how it is if you consider from the perspective of the sampling that we are going to talk about, it is in a way that we are kind of taking the inner product between the signal and with a particular standard basis. Okay. But in such kind of framework, when you sample this sparse or the locally sampling, we need to capture each and every point in the space. Of course, each acquisition or each such measurement has a cost. So we want to reduce the measurements. So of course there are theories have developed that how we can reduce such measurements, but again that is developed with a certain notion of the signal, that is smoothness, or you can say that slowly varying signals, or in more simpler sense you can put it into perspective of frequency domain analysis, that we're looking at the low pass signals. But here we deviate that when you come to such kind of sparse signal, is this local measurement going to be good choice for a sparse signal? It is a good choice provided we are not interested in minimizing this cost of measurement. So let's take a example. I mean, that was from the history at the World War II, where the CS would have first taken place. Okay, so this is an example in World War II where syphilis was a big problem, and US Army wanted to test each of its soldiers for syphilis. And you know that not everybody has a syphilis. This is as a kind of a sparse signal. So if you construct a signal with mapping the soldiers in order and position of a person which is having syphilis at 1 and not having syphilis at 0, it's a sparse signal. So now the question comes, how can you manage such a huge population with limited number of test kits? Well, this problem is now even relevant in today's context, at least this pandemic situation, where now the situation has improved, where the number of test kits are limited, but you want to test a huge population. So in such scenario, somebody can suggest, can we just do a random sampling of the population? Then we have an idea how much people have got the infection. But to be honest, random sampling is not a good choice. In fact, we may miss all the positive cases. This is an example I'm just illustrating. So what I'm trying to tell you that even if you come up with reducing the number of measurements by randomly pressing the samples, it is still going to not give us what you want. So it's not a good idea that randomly picking the samples. So the best thing that we can do here, I mean, we haven't done that. In fact, US Army has done that yet. So what they have done, so they have done a pool testing. So what is pool testing? So a smart person come up with an idea that instead of testing the entire population one by one, can we make a pool of army men and draw the bloods together, mix them up, and we test for each of such pools. So it is like if you see this rectangular blocks that I'm trying to represent this samples, basically is a collection of samples that forms a pool. So in the process, if you keep testing all these pools, wherever a syphilis positive person is landing in that pool is going to be tested positive. So that way, no way we can miss the person who is positive, or at least we cannot miss a pool which is positive. So once we detect the pool which is positive, a further finer test can be done to identify individual person. So this could have been the first example in a way of global sampling. So I call it as a global sampling, or you can say the first notion of compressive sensing that introduced into the field of statistics or signal processing, you can say that. So here, but unknowingly, I must tell that unknowingly there exist many such acquisition process. If you try to interpret as a sampling, in particular in the field of imaging, they do the same way of global sampling. For example, if you consider this CT scan or the tomography, this tomography imaging is nothing but we take the measurements of the line integral of the space. So similarly for MRI, it gives basically the Fourier, it basically gives the coordinates of the K space or the frequency components of the space. So it is in a way global measurement. It is for the case of tomography, it's the inner product between the line in the space with the actual scene that we are going to observe, or in this case a slice of a person's body. Same case for the MRI. So, but in MRI it is a more of a sinusoidal measurement. So now what we conclude that for sparse signal, dense measurement or the global measurements are good as long as the signal can be reconstructed back. That part we haven't put it as a constraint. So far we have mentioned that of course for syphilis test it was clear that how the strategy is to reconstruct back and what kind of a measurement strategy we have taken. But in general, when you say that global measurement or so-called dense measurement, we haven't put a constraint yet, the reconstruction. So now we first going to discuss now.
Yeah, Sujit.
Yeah.
There is a question from the participants. Would you like to engage them during the session, or you would like to have the questions later?
Yeah, I can take on. It's not a problem, but I mean, it doesn't necessary that we have to cover everything as long as people are getting something here.
Yeah. Yeah, Ranjan, you can go ahead.
Okay, good morning, sir. My question is just you have started discussing this sampling. So you are emphasizing entirely on image processing a kind of stuff. So is this compressed sensing is also applicable for signal transmissions and all?
Well, I'm going to introduce the theory of signal process, theory of compressed sensing. So my examples are probably, if you see, that probably comes from the 2D signals. But of course, syphilis was a good example of 1D signal. So without loss of generality, you can always look into applications where we can extend this to 1D signal. For example, if you consider this global measurement as a mixing process, okay? So it's basically I'm talking about inner product. Consider it as a signal mixing. So there exists technique where people acquire broadband signal by mixing the signal with a known signal pattern. So I haven't put this example. Probably images are more illustrative for me. I mean, as a person working in imaging, otherwise I could have put some 1D example though. But if it's difficult, my objective was to deliver the essence of compressed sensing. If you already only look for 1D signal or kind of application to communication, probably you have to hang on a while till we reach the end. Then if you are confident that the CS works, probably you yourself can come up with examples.
And one more thing is, am I audible, sir?
Yes.
So one more thing is that you just give an example of US Army and regarding this pool test and all. And you comment that in our India during the pandemic we are not do the random testing and it should be like cluster this group testing. So this group testing is quite equivalent to that of the cluster testing and all.
Well, this Indian context, I won't say particularly this COVID-19 pandemic, because there is no way you can mix the sample and really declare one cluster as positive, because it's still an individual test at this stage. Okay.
But
so
in earlier we are projecting that it will start from the south and then it move towards the north and all. So there was a pattern of has been developed and it has been published lot of media channels and all. So how could we not say that we also did the cluster sampling in during this pandemic?
No, I'm not saying that it's not it's a bad idea or so. What I'm trying to tell is that the difference between the process.
Yeah, okay. Yeah. So, just 1 minute. So Ranjan, the point what the speaker has made and the context you are asking are totally different. The army context, the problem. No, let me complete. The army problem, the objective is to identify the group and then isolate them so that they are not going to participate in the war. But in the pandemic test, if you make a pool test, you can do that in the emergency cases. But if you take 100 pool tests, if you want to isolate 100 of all of them, your logistics is a big issue. So that concept was something like in a different way. The problem is if you want to know that, you just search in the Wikipedia and you will come to know more about that. But the same strategy you cannot straight away take into the pandemic situation and take the full test. Yeah, Sujit, over.
Okay, thank you.
Okay.
Thank you, sir.
All right, so can we move on then?
Yeah, Sujit, please.
Okay, so we were talking about this global measurements and the uniqueness of this measurement, whether we can reconstruct back this signal from its measurement. So in CS, typically the dense measurement that we're referring mostly look like this. The pattern that we're going to use to sense the signal are random. Okay. But it is not a binding. There are other techniques there where we not necessarily requires the other constructions where we don't require random patterns. But for good theory that has been developed for CS, mostly look at this random patterns. Okay. And CS guarantees that sparse signal may be constructed back from its measurement. That is the beauty of this compressive sensing. So this has a strong theoretical backing. And further, CS requires less number of measurement compared to conventional sampling. Of course, we agreed from this sparse signal example, if you really want to do the conventional sampling and reconstruct back a sparse signal, we cannot really avoid the dimension. We have to take the measurement as same as the dimension. But whereas this dense sampling or the CS has the opportunity, gives us an opportunity to minimize the number of measurements. Okay. So now let's look into what finally we're going to deal with. So more mathematically, the problem look like this. So we have a sparse signal of dimension d. It may not be sparse by itself. It can have a transform, orthogonal transform for simplicity that can make it sparse. And it has a sparsity of s by itself or in the transform. And then what you are interested in, making some measurement m measurements for this d-dimensional signal, where m is much smaller than d. And the idea is from this m, we want to reconstruct back the original d-dimensional signal. So this is a typical CS schematic look like. Okay. So now the problem is the number of measurements. So we have already seen the schematic is basically a fat matrix. So number of columns are more than the dimension of the columns. So measurements are few. So can we reconstruct back the signal from Y? So that's a big question. So let's take this example. For this toy example, we have this measurement matrix A, and this is the signal of interest that we want to reconstruct back, but we don't know what it is, but we only know the measurement. So what are the choices we have here? Since the number of equations, we have to solve all these 4 equations, but unknowns are 6. So we have infinitely many number of solutions. It's a typical inverse problem, which is not giving us a straightforward closed form solution. So what is the remedy out of it? What can we really do so that we can converge to one solution out of this infinitely many solutions? So let's take the same example and look for this solution. This is one of the solutions. You can check that probably. Yes, I think this solution admits to this particular measurement. Okay. But this is not our signal of interest, because we said that we are going to do this dense sampling or compressed sensing to reconstruct the sparse signals. So what we are interested in the solution which is sparse. But before going into any conclusion, we should first see or characterize the solution to some kind of quantity. What we should first find some kind of quantitative measure for this kind of solution, so that we can converge to a true solution that we are interested in. Okay, so let's come up with such measurement, some kind of a number out of the solution. let's say call it this 3 norms that we are going to compute of this solution vector, namely the L0 norm, which essentially calculates the number of non-zero entry in the solution. And one is L1 norm, which is going to tell us the absolute sum of the entries of this vector. And L2 norm, the square sum and the square root of the sum of this entries of the vector. So let's evaluate this number or these norms for this solution vector. So what we see here, the L0 gives us 6. That means, of course, all the entries are non-zero. So 6. L1 norm is this one, and L2 norm is this. Okay. Similarly, another solution admits to this particular measurement is this one. I think you can verify it's straightforward. So what are the norms for this solution? L0 norm is 1, L1 norm is 2, and also L2 norm is 2. Okay. So the solution what we are looking at in this particular measurement is actually this, because we said we are interested in the sparsest. We are basically measuring the sparse signal. So we're looking at the sparsest solution. So to solve such such situation, when the number of equations are less than the number of unknown, when we have this infinitely many solution, so we should find a criteria to, eliminate all possible solutions and converge to a good solution, that is the sparsest one. So L0 norm is basically the solution that we are going to look at. But then the question comes whether this L0 norm, or if, let's say, I give you a sparse signal, can we just reconstruct for any measurement matrix or any kind of dense sampling we do for a sparse signal, and we use the L0 norm as a criteria for reconstruction? Is it possible for us to always uniquely reconstruct back the signal? That uniqueness we yet to answer. Okay. So this, under certain conditions, if you put on this sensing matrix, or I say that this, compressive measurement, then with certain number of measurements and certain kind of structure into the matrix, it is possible to reconstruct back the signal, any S sparse signal, where S is smaller than, of course, at least I must tell you that there is S should be smaller than M by 2. Okay, that is a requirement. You will see in a while why this requirement is going to come into play. Okay. So now let's assume that that this requirement is satisfied, the measurements are unique. So then how do we acquire the signal? The sensing component is, as we have seen in the sensing box, is always y equal to ax is the sensing. And the reconstruction is, we are looking for the smallest L0 norm solution from this linear system of equation. Okay. So that's how a typical CS workflow is. So you take a sparse signal, you acquire through this dense sampling matrix or measurement matrix A, and then after you get Y, you want to reconstruct back the signal X from the measurements with this objective. Okay. So as we have already seen in the example, not all signals, whether be it in the transform domain or by itself, not always sparse by itself or they exactly sparse in themselves. But what they have mostly significant entries at only few locations, let's say S significant entries, but the rest of the entries are like very insignificant. We can assume them as to be 0. But in real life, we may not have such true sparse signal which are truly 0 elsewhere except from these S non-zero locations. So when we have these insignificant locations at present, so we can always split this vector, okay, this nearly sparse vector U, into two components. What we said, X is carrying the most significant S components and U is the non-insignificant components. So that serves as an error. So X is actually the true signal of interest, and E is basically comes from this measurement as an error that is coming from this insignificant coefficients. So, and what assumption we have to take here, since we have termed it as insignificant, it has to be the norm of this error has to be bounded or has to be very small, so that we should be able to reconstruct back the signal. So in such scenario, also another scenario where such problem arises when your measurement matrix get corrupted by, when you a measurement process get corrupted by some noise. So when you are dealing with electronic system, let's say I was talking about MRI or CT, or let's say even you are talking about a true compressive sensing for the broadband acquisition. So in such scenario, your electronics noise, all sorts of noise can come into play. So there also land in a situation of this error vector presenting in the measurement. And again, as long as this error is bounded or isn't having the limits, so we can always reconstruct back X using this objective, that having the smallest L0 norm of the X, and that satisfy this condition. In such scenario, the reconstruction problem become like this. You acquire the signal. Of course, you don't have the exact knowledge of E, but we know the characteristic of E. Or more plain language, you say if it is additive Gaussian noise, you know the variance of E. So in such scenario, if we take the measurement Y, and the reconstruction process can work by solving this L0 minimization problem. So the information we need, the measurement matrix, and of course the epsilon that is needed, and then we can reconstruct back the signal X. So another situation is that when, as I said, that I have to introduce that when there is not, the signal is not sparse by itself. So let's say the signal is sparse in a basis psi, and we don't take it as assume it as an orthogonal basis, but it's an invertible and the basis, the set of vectors. So X has a representation that is U, which is sparse, and we are measuring Y using the sensing matrix of the that global measurements AX. So from Y, if you want to reconstruct back X, so the solution would be that instead of optimizing the finding the solution that satisfies the lowest L0, smallest L0 norm, we should actually look for which is having the smallest L0 norm in the inverse of this matrix psi, or the transform psi. Okay. Otherwise, we can also solve the same problem. If we explicitly want to solve for sparse problem, then you replace X with psi U, and then that become a new measurement matrix. So if you combine these two, let's say A hat, so that become a new measurement matrix, and we can solve back the this optimization problem, and then we can come to a solution X equal to psi times U. So in this scenario, the measurement and the reconstruction process look like this. Okay, but here I must add that I haven't probably I haven't contained the slide for the noisy measurement. So here again the noise can be, or the insignificant coefficient can be added in the same manner that we have seen for the sparse signal by itself. So you just need to add one error vector here, and the minimization problem can work like the same way that we have seen before. So we assume that the unique measurement exists, and then we talk about that the process of CS that we're going to go through, and this is actually the essence of CS. That's what I must tell you. But then the practical aspects and all the workable algorithms will come later. But before this, we have taken an assumption that the measurements are unique. But the condition under which it is unique, or what kind of criteria we set on the measurement matrix, we haven't defined. In today's lecture, we'll only see two intuitive measure that will tell us that what kind of measurement matrix will helpful in acquiring the unique measurement. So here, yeah, we are interested in solving this uniquely. Okay. So let's take a practical example. I mean, our what do we call that? The previous sensing matrix. I think it is the same sensing matrix we are showing here, but with a different measurement. And we see first what is the problem of uniqueness that we are going to have for a particular sensing matrix. So let's say this is the sensing matrix that we have already seen before. And we don't know the unknown sparse vector, but what we are telling that here we are measuring a 2 sparse vector with sparsity 2. And it's admissible sparsity because the dimension of the vector is 6. So we are interested in measuring a 2 sparse vector using this sensing matrix. And this is one of the measurement we have. Can we say that this measurement is unique? That means you must admit a unique 2 sparse solution, right? In this case, probably yes. This particular X admits this solution, but certainly I cannot verify the uniqueness unless somebody can come up with a counter example. This X is not unique. But it's a lucky measurement and a lucky signal for which I have a unique measurement. But what about this? In this measurement, I can tell you that there are multiple signals that map to the same measurement. But again, the sparsity is 2. We didn't change the sensing matrix. But suddenly, it's not universally true for all 2 sparse signals. This sensing matrix is going to work. Okay. For example, this particular measurement Y admits this signal. Okay. We can see that this signal, if you multiply X with A, we're going to get this Y. Similarly, this signal also admits the same Y. So no way we can ensure that all kind of 2 sparse signal can be reconstructed back using this matrix A. So how can I check this matrix is good enough for my required sparse signal to be reconstructed back? So I need to put some condition. We need to put some condition on this matrix so that we ensure there is no ambiguity on the measurement, and while at least reconstructing back the sparse signal with a known sparsity. Okay. Uniqueness of measurement is highly desired. So this is the theorem. This is the smallest little theorem that tells you that these measurements can be unique as long as the condition on A is this. The spark of A is greater than 2s. So here S is the S sparse signal, the sparsity of the signal. So if we want to make sure that all our S sparse signals have a unique measurement in a matrix A, so we should have this property in matrix A, that the spark of A should be larger than 2s. Now we'll come to ask that what is spark. Spark doesn't have a standard definition in linear algebra theory, but it has a definition like this: the smallest number of linearly dependent columns. Okay, the smallest number of linearly dependent columns. Carefully, we have to watch this. It's not a rank. We are not asking for the number of linearly independent columns. So what we are asking here is, you take, so basically our sensing matrix carries d number of columns, and each column is of length m. So how many columns, what combination of columns you can take?
Sujit, one of them has a question. Can I allow him?
Yeah. Sure.
Yes, Ranjan, please go ahead.
Sir, my question is, how we ensuring this sampling at the time of data acquisition?
Which data acquisition you are referring to?
Means you are saying that you, in the previous slide, you have shown one matrix A. So that are supposed to be the input matrix, right? And out of this input matrix, we select randomly, means take some samples. Those are the sparse samples we are saying.
No, sorry. So can you just slow it down? I mean, I'm not able to catch your question. Yeah. So
okay, I'm just asking that because see, once we have all the data, then we do sampling, right? And this sparse sampling, you are saying that at during the data acquisition time itself, means in the almost in
okay,
the
let me
real
clear
time.
your thoughts now. Okay, so you're right. So I understand. So what you are trying to tell here is that, so in all this thing that I'm discussing, your signal is discrete. That is what your concern is, right?
No, my concern is that we do sampling once all the data is there. Okay, but
Huh?
once you said that at the time of acquisitions we can
Uh-huh.
choose samples, right? Those are the
Yes.
sparse samples. We are not going to collect all the values. We are not going to collect all the values. Means we are
No. I never said
taking.
that we have to choose. We have to choose the sparse sample. I think you misinterpreted me. Okay, I understood what is your concern. Okay, let me go back to my first slide. So that will make it much clearer, I think. Okay, so if you recall this wavelet, in this wavelet scenario, I have ordered this basis. Okay, so I just reorder this coefficient from decreasing order. You see, around 10% of the signals are actually significant. So I'm not saying that you should know the position of the samples where that is insignificant. We need not know, but we should know, or we at least know that the number
So
of significant samples in this
how
particular signal are much less than the dimension of the signal.
so first we should have need to know about the dimension. Then
Yes.
accordingly we do some prediction that on these positions or
No.
these
Again,
specific time.
again, I'm telling you, position we need not worry. We need to only worry about the numbers. Whether the number of significant coefficient or significant entries are less than the dimension or not. If they are not less than half of the dimension, we cannot declare them this as a sparse signal. Of course, you are referring this entire discussion by starting with the definition of the sparse signal. So as long as our signal doesn't fit into the category of sparse signal, all these theories doesn't work. Okay.
So
Either it has to be
this
sparse
theory
or sparse on
consists.
the basis.
So by this theory we have taken into consideration the threshold value as well as the a number of count of which we have taken in the sample. Both these means both these two parameters will be there.
Just a minute.
Means
Let me
threshold
take this call. Sorry. Why is calling regularly? Hello. Raghavendra. Yeah. Good morning. Yeah. Tell me. Yeah. Can I? I'm in a lecture now. Can I call you after 2 hours? So I will call you after the lecture. Okay. Yeah. Sorry. So what was your question?
My question is to be a sample in a sparse set means there are two conditions. One is that signal must have the less the total less than the half of value, as well as the and the count number of count is also the predominant factor to be the sparse sample.
What is number of sample you are referring to? The signal number of non-zero entries in the signal, or the measurement you are talking about?
Number of non-zero samples in the
Yes,
signal
there
means
is a thumb rule that number of non-zero entries or the significant entries in the signal has to be less than the half of the dimension of the signal. Then we declare it as a sparse. Okay.
okay.
So let's say you have 100 signal of length 100. So your number of non-zero or number of significant entries should be less than 50. Okay.
But out of those 50 further the number of means these values are above the threshold, let's say
Right. These
let's say
values are above the threshold. Yes.
and then out of these 50 100, is there any minimal number of count just you are saying that we have to taken into consideration, or all these 50 values
No.
will be.
So see, we have to define like what kind of sparsity is admitted by this class of signal we're going to deal with in our application or in our particular problem of sampling. If we define that number of significant entries are S, so I quantified as S, and this S I have told that this S is a number which is much smaller than d by 2. So S is much smaller than d by 2. Okay, I would say smaller, much smaller than d by 2. Okay.
So this sampling do
That
not
is the
bother
only thing
about
you require.
whether the inputs are coming on the regular basis or some random basis. This consideration is
No,
not
no, you
there,
don't
right?
need to worry about where. If you know where the samples are, then our problem become easy. So there is no much
Yes, of
question. So we don't know where exactly the samples are. Okay. So
okay.
that's why we are making a global measurement, right? So we are acquiring the signal through a dense measurement because we don't know where the samples are. If we know where the samples are, I'll exactly go to that position and acquire the samples, right?
Definitely,
So,
definitely, definitely.
so I don't need to really do a dense sampling.
Yes, yes. Thank you, sir.
No worries, yeah. So, yeah, so I think we are somewhere here. So here we see the situation that uniqueness is not, we are seeing, and then we come to the definition of Spark. So Spark says that any submatrix you create out of this matrix A by selecting number of columns. So what are the possibly smallest number of columns you can choose that can make this number of columns dependent? Okay, so that is the value called Spark. So as long as this value is above twice the number of the sparsity S, then it can ensure us that all our measurements for the sparse signal are unique. Okay, we'll see in a while the proof. So let's assume that we have another solution apart from X. So we know the original signal X is of sparsity S. So now we assume that another signal we have V, which is also admitting the same measurement Y. Sorry. So A times V become Y. So if it is true, and this is a sparse signal also, so that means there's a situation where we are not sure whether this measurement for X is unique. Okay, but we are telling that our matrix is admitting this sparse condition. If this is the condition, then we'll prove by contradiction that it is not possible that B is another sparse signal. We'll see in a while. So if V admits the measurement, X admits the measurement, then AV minus AX going to give me a zero vector. So what in a sense we are going to tell that A times V minus X is going to be 0. So what does it mean? See, V is having this, for this illustration, if you see this is a matrix, what I'm trying to tell, a combination of these two columns and a combination of these two columns are going to give me the same vector. So if I arrange them this way, V minus X, then I'm going to get a zero vector. So what in essence I'm trying to tell you that I have another vector V minus X, which is of, what should be the number of non-zero entry in V minus X? It should be 2s or less than 2s, right? So V minus X should have number of non-zero entry less than 2s because X having the non-zero entry as S and V having the non-zero entry as less than S. So if we combine them, so total number of non-zero entry is going to be 2s or less than 2s. And what we are essentially telling that we have a combination of columns in the matrix A that is less than 2s, the less than 2s number of columns, that is going to give us a zero vector. What does it mean? That means the less than 2s number of vectors are linearly dependent. Okay. But is it going to be true? Because what we say that we started with the condition that the matrix admits the spark greater than 2s. That means this matrix cannot have any 2s or less number of vectors that can be linearly dependent. So they are contradicting each other. Okay. So what could be the answer then in this scenario? So is there any another solution that exists which is less than 2s? So no, less than s. So we cannot have a sparse solution which is less than s. So for any s or less than s sparse vectors, if we have a sensing matrix whose spark is greater than 2s, it ensures a unique measurement in L0 norm recovery. So you want to recover the sparsest solution, that is going to be the unique measurement. Okay, so let's check our sensing matrix A that we have been looking throughout this lecture, that whether this admit the spark condition or not. So for we have checked that one of these two sparse vector giving us non-unique measurement. So that means this matrix should not have a spark greater than 4. Okay, so let's check whether that is true or not. Clearly, if you take this combination of these 4 columns, they're going to have a 0 solution. So that means the spark of this matrix A is not larger than 2s. It is somehow lesser or equal to 2s. Okay. So that concludes that this measurement matrix is not suitable for 2 sparse signals. Okay. Now, another property of a matrix that we are going to introduce that is further going to quantify. So we have seen the spark. I would say this restricted isometric property is more of a quantitative measure. So you can say that the spark is a qualitative measure of a matrix. So this is a kind of a quantitative measure of a matrix, further refining the concept of spark to give us this form. So that is the restricted isometric property. So what we are saying here, so any matrix, measurement matrix A, and we take L2 norm of any S sparse vector AX, and then they are bounded. So what we're trying to tell, that you try to transform or take a measurement of any S sparse vector. You create a space of S sparse vector, and you take any vector and take this measurement AX, it is going to be bounded. And what is the what is the boundary or what is the limits of this measurement? The norm in L2 norm. So the norm of this measurement vector is upper bounded by 1 plus delta S times the norm of X, and lower bounded by 1 minus delta S times norm of X. Okay. So where delta S is termed as the restricted isometric constant. Okay. Or simply we call RIP. So what is our intelligent guess for delta S? What value the delta S can take? Can it be a negative value? Can delta S take a negative value? Since we are talking about norms, so what is the basic criteria of norm? Norm has to be a positive quantity, right? So if delta S takes a negative value, can it still admit to a norm? First of all, this inequality will not satisfy for a negative quantity. Will it satisfy for a negative quantity? Because we're going to tell that this norm is greater than some value of X and less than some value of X. So it has to be greater than 0 and less than 1. Okay. What if it is becoming 1? 1 is still admissible, not a problem, but cannot be greater than 1 or cannot be less than 0. So what in a sense we're going to see from this RIP is that, a restricted isometric property is that, so when we're having, we can have a choice of X among this, if I design a vector space or kind of a set of, I would not say that vector space, but rather I would say a set of vectors which is of sparsity S, I can have such X where Ax is larger than X. X is larger than X means I'm referring to the length, because we are talking about L2 norm here. So the length of measurement is larger than the actual signal. In such scenario, we are hitting the upper bound of the rip. So how much larger? The largeness is bounded by 1 plus delta S. Similarly, we can have a such X which can have a smaller measurement than the X. But how much smaller is lower bounded by 1 minus delta S. Okay. And what is the smallest possible value of delta, as I said, could be 0. So what does it mean? When which condition we can have that? So that means the measurement doesn't change the norm. I think the best answer to that is if A is an orthogonal matrix, we know that norm is going to be preserved. Is it orthogonal is sufficient or orthonormal? So as long as A is an orthonormal matrix, that it carries all unit norm vectors and orthogonal to each other. So in that scenario, we'll end up in X norm as same as norm of X. Okay, but X we cannot guarantee it's because X is a subset of the vector space Rd. So since X admits the norm equality, so the sparse solution will also admit. But anyway, we are not worried about the equal norm, but we are interested in as long as this is bounded nicely. So that is what it essentially telling us. It is essentially telling us that any submatrix we create, because we are talking about X is a sparse vector, right? So X is a sparse vector means we are talking about A times X means we are basically creating a submatrix out of this A. So if you are taking any submatrix out of A, this submatrix is going to be a norm-preserving matrix. Okay, it's a good matrix, or it is an invertible matrix because it is bounded by this. You cannot find such X which can make it 0, because as long as del S is non-zero, that's what I'm assuming. So in a sense, it is refining the notion of the spark that we have started with, so that any S column you take from this matrix, they are going to be linearly independent. A larger number of vectors, smaller number of vectors, S or smaller vectors, number of vectors you take, they're going to be linearly independent. So to ensure that any S sparse signal has a unique measurement, so what we need a reap of order 2s. Why? Because 2s is going to give an equivalence of spark of 2s. Okay, so we've seen the proof for spark of 2s, right? So we need at least that the spark to be 2s. If you want the spark to be 2s, we want the reap to be follow of order 2s. So that will ensure that no 2s or less number of columns or submatrix form out of this matrix A can carry linearly dependent columns. And if that is true, that makes sure that all S sparse measurements are unique. Okay. So again, bringing us to this concept of what is essentially mean by this largest AU. This delta 2s gives us that what is the largest magnitude of the measurement I can have. In other words, it is referring to, if you recall, the matrix norm or the induced norm of a matrix. That is basically how much a matrix can scale a vector, right? So that is lying on the singular value of that particular matrix. So if you take all submatrix, all possible 2s submatrix, and what is the largest singular value you find among this matrix A, that basically represent this quantity. Okay. And if you find that singular vector, of course, the submatrix I am referring to. So that submatrix which is having the largest singular value among all submatrix is basically this quantity. This is the largest singular value among all possible submatrices. And the vector, the singular vector associated with it, is going to basically give me the largest scaling. Okay. So So this is the more, so we have introduced two criterias. There are many other criterias, including coherence and mutual coherence and other things are there. But with this, we are kind of happy that at least our LGO norm is going to give us a unique solution for the measurements as long as these two conditions are satisfied. Now, what are these matrices that can admit the restricted isometric property or that will obey this sparse constraint? So what are the possible construction of the matrix? So is one construction of the measurement matrix which actually admits this RIP. That is random, a matrix, you take a matrix of dimension m times d, and each entry is a random Gaussian sample, or you can say that entries are IID, random Gaussian variable. So, and the variance is 1 over m, and the 1 over m is required to make sure that the measurements are of unique norm in expectation. So, another such measurement is this Bernoulli or Rademacher matrix. So, each entry is a random variable coming from Bernoulli or Rademacher distribution, again identically distributed independent random variables. Gaussian random matrix and Bernoulli random matrices are very good matrices for this compressed sensing job. Okay, and in fact, somebody asked me in the beginning, are we going to really deal with only images, or we are really going to talk about some real application in communication? I think this random Bernoulli is one of the such matrix that has been heavily used in communication because of its nice properties, and at the same time it is coded with only binary numbers, so it doesn't need to really have large number of what is called that dynamic range to code such a measurement matrix. And it is also used in coding theory. I mean, in channel coding, people have used such matrices. Okay, we'll see one example towards the end, if possible. So another such matrix is that admits this RIP and this sparse is structure random matrix. So what is structure random matrix? That it is basically a Topli's matrix. You can take first example of the structure random matrix. Topli's matrix are created like this. You have a vector, d-dimensional vector, and you keep shifting. It's a linear shift. So each time it shifts out, a new vector is getting added. A new entry is getting added. So this Topli's structure is created. So like this, we can create a D cross D Topli's matrix. And if you take any random rows out of this Topli's structure, that will serve as a very good sensing matrix. But again, this is not a fully random matrix because there exists some kind of correlation among the entry, because all entries are not unique, because it is basically circular, linearly shifting the entries. So, but still it admits RIP, but the number of measurement in such case may be larger, bit larger than the regular random entries, but it admits RIP. Similarly, another structure random matrix is called circulant matrix. So here, instead of this linear shift, we do a circular shift of the random vector. It is even more space preserving, you can say that. And many of the occasion, if let's say, I don't know, I'm not a communication guy, I mean, I haven't worked much in the communication problem. Okay, slowly with colleagues like Dr. Nilkandan, I'm looking into the problems. But in communication system, most of the time you will encounter such circulant matrix with random entries, if possible. I don't know, maybe in channel estimation scenario or so, where you have such scenario that you possibly come up with this circulant structure. And such matrices also nicely admit to the RIP. But again, these entries are crucial. I must say that this is random, assuming that the random entries. Okay, if it's not random, you may find that for some, if you are there, all carries equal values at some level, not some level. It is going to be actually all the circulant doesn't going to change anything in the structure. So the spot, in fact, the rank of the matrix is 1. Okay, so this is critical, that the entries has to be random in this vector. And some such example that I said, the random deterministic matrix, why I'm coming here, we start with the partial Fourier matrix, because I have already started the introduction with a nice MRI measurement which takes this sinusoidal measurements, is essentially taking this random Fourier measurement, not random in sense of in the case of MRI. Now they have come up with the random, but usually they take this the radial measurements from the K-space. Okay, so this is what you construct a Fourier matrix, D cross D Fourier matrix, and take M random rows. So that in a way gives us a sensing matrix. That means you are measuring the signal by, taking the inner product of the Fourier basis with the signal. Okay. But in the random inner products you have been accumulating. Okay. So that also admits order of 2 REAP with, but it's also true that it's not only for Fourier, it is also true for all sort of orthogonal matrix. If you choose random rows, they can exhibit some degree of, up to maybe the number of measurements are larger in that case, rather than the completely random matrix, but they admit the RIP. Okay. So advantage of structured matrices, be it random or be it this deterministic structure matrices, is that the measurements become easy, because since they admit certain structure, we can actually design the measurement in a more efficient manner. So, and less number of storage space if you want to transmit the measurement matrix. Of course, if it's a parametric matrix, you need to only give the position of the Fourier basis. If it is a circulant matrix, you need to transmit the vector only, the only d-dimensional random vector. So such way your storage requirement reduces. Of course, as I said, the efficiency of taking measurements improves. Okay. So till now, what we have covered is that we have seen some example of measurement matrix and the condition that requires in the measurement matrix to ensure a unique measurement. Okay, so let's assume that the condition is already taken care. The REAP of order 2 is satisfied. Now what next? We have taken the measurement. The next big question is, what are the practical way that we can solve this problem, L0 minimization? It looks nice from this toy example that you can solve for all possible solution and pick up the sparsest solution. But what is the real problem? This is a good news, that recovery is guaranteed with REAP and with Spark. But the big problem comes from this. The bad news is L0 minimization is a troublesome procedure. Because if, let's say, I told you, even apart from L0, I give you additional information that the signal is of sparsity S. So what do we have to do? Essentially, we have to get all possible solutions out of this infinite solutions. That is, how many solutions possibly? If I just want to find the non-zero entries, irrespective of the values, the combination is go like the D choose S, right? And it is enormous number. And out of this, I have to pick, the sparsest, the solution that satisfies the smallest, that admits the smallest L0 norm. Anyway, so that is one issue. So it's not practical that we can solve with L0 norm. So we have to come up with some strategy to solve. So there have been a lot of research has been done in this area. So majority of if you channelize them into, it comes under these 4 categories. Okay. So to achieve this goal, we have taken these 4 paths. One path is this. This is this convex relaxation path. We will discuss this in a bit of extension today. And also we'll cover this, one of this. It's not that there are a lot of algorithm existing this. Of course, this is the beauty of L1, what we started the compressed sensing, but later on more practical algorithms converge out of it. So, and another, this greedy iterative pursuit, we'll take one example, that is OMP. And I will not touch upon this, but there are also existing these methods, the LP norm minimization, non-convex minimization algorithm that achieves the better solution at some instances. So again this combinatorial that we discarded in the beginning. There are some smart way to avoid this combinatorial problem, and they have come up with some practical way to solve this algebra normalization problem. Okay, so our target is this two today. So let's start with this convex realization first. Reconstruction, so we will replace this L0 with L1. So now we have to make sure that we have guaranteed for L0 that L0 norm we can recover uniquely, L0 norm minimization can recover uniquely the measurements from the measurements provided this spark and this order of 2 repeats, the 2s repeats satisfied. But then we are now changing our goal. So instead of L0, we have now introduced L1. So let's first see whether this L1 is actually a sparsity inducing or not. So let's get a geometrical or intuitive idea about L1. Then we'll see at what condition this L1 also going to help us getting a unique sparse solution. So this is the change in statement, problem statement. So now we have replaced L0 with L1. So what essentially we're telling here, that if you take a space of solution that is AV times Y, so Y is the measurement and A is the measurement matrix, and V is all such vector that admit AV equal to Y. Well, I have mentioned it null space. It's not truly null space because it's not a space. If you write such solution as a collection of vector, it doesn't probably satisfy the all axioms of vector space. However, if you consider this as a affine space, which basically a translated version of the null space, where the null space that admitting the zero solution get translated by the actual solution X. Okay, so this is basically this plane represent the space carrying all possible solutions of AV equal to 1. Now, what you are looking into, we're looking into a minimization problem. Earlier we saw that the L0 minimization. Now we're looking into L1 minimization. So what we essentially will do, we'll see a unit sphere or unit ball, that is the ball or that is the unit radius circle form in that particular norm, and we're going to expand it. And when it meets that plane, that gives us the solution. Okay. Let's start with L0 norm. Well, L0 norm is a infinitely pointing norm, if you see, because it's just pointing. It doesn't have really. You just count the number of non-zero entries, right? So that's how the ball look like if you consider L0 for sparsity and L0 norm equal to 1. Now, if you increase the norm of L0 by 2, so this transform to this axis to the planes now, because planes have dimension 2. Because this example is in a 3-dimensional example we are looking at. So if you're looking at sparsity 1 or well L2 and then 1, it is only the axis. For 2 is the plane. Okay. So now if you look at LP ball, where P is less than 1, it's not a norm, but if you still try to use the definition, the standard definition of norm, and try to construct this function, it look like this. This is the ball that this is pointing outwards. And similarly, L1 ball is basically absolute value that we are looking at. So for 3-dimensional space, this look like like a cone. It look like this, not exactly a cone, but it's a unit sphere for in L1. Okay. Similarly, of course, L2 ball is like truly a ball, because the sphere is defined in terms of distance in the Euclidean space. So Euclidean distance. So that's why it looks like a sphere. But this is an abstract. Is the abstraction of the concept of sphere to different norms. Okay, so now let's see how the solutions admit in the case of L0 minimization. Okay. For L0 minimization, so this is like pointing arrows, and then this unit ball, they're going to see where they're going to hit the sphere, the plane that is carrying all possible solutions. Well, this correct solution is only admitting why, because I said that only when m greater than 2s. That is an important criteria that we have to mention. That when I say that the number of submatrices, this is 2s and the submatrix measurement is m. So we say that any submatrix created out of this measurement matrix is not linearly dependent, okay? Anything less than 2s. So what does it mean? It necessary that m has to be greater than 2s. Otherwise, if m is not greater, the number of measurement is not greater than 2s, we may land in a situation where there are already, null space existing, or the non-zero. I mean, there exists a linear dependency among these columns. Okay. So this is a criteria that has to be mentioned, but it is applicable for all of them. So it's not necessary that you should avoid for all. So similarly for L1 ball, if you now expand this L1 ball that is meeting the space or this particular plane of solution, so that is basically your solution. Here in this case, this is also the solution that you are getting. But this is giving a sparse solution, and this is also giving a sparse solution. That is only one-dimensional solution here. Means one entry in the three-dimensional space. But when we go for a L2 solution, it is not going to give us a sparse solution, right? Of course, you can argue that if I have the axis of the plane which is perpendicular to the axis, in that case I can hit a sparse solution. Well, that is fine, but that is only one instance where L2 will admit a sparse solution. But if you consider measurement matrix and this construction as a uniform design, you cannot guarantee for all possible vectors. But however, this guarantees, of course, there are also ambiguity present in this line, but that ambiguity will be taken care with certain condition on the measurement matrix. But in general, apart from this particular ambiguity, it always admits a sparse solution. So before going into the analysis, so next thing we'll see that what further constraint we can add into the measurement matrix so that will ensure that our L1 minimization problem will give us a sparse solution, or in other words, it is so all sparse measurements that we obtain from this measurement matrix or the measurement we obtain for all sparse signal will be unique in the L1 minimization scenario. Okay. This is called the null space property. So we have introduced another property of the matrix here. In a while, I will show you that this null space property is a further restriction added to the RIP. So if you put a condition or a constraint to the RIP value, the RIP constant, that will ensure that null space property is satisfied. But without going into that, let's first assume that there is something called a null space property of a matrix. If this null space property is satisfied, then, as I said, this L1 reconstruction will give us a unique solution for all such M-sparse or S-sparse signals. Okay. So what is basically tells us that, so apart from the sparse solution, consider any other solution that we come across. So if you take the difference, we are going to get a null space vector, right? We have already seen such construction where we have taken AX is the actual solution and AV is the any other solution that admitting to this system of equation. Then AX minus V basically is your, where XB is your null space vector that admits to 0 vector. Okay, A times the null space vector will give you 0 vector. So what condition essentially is telling this null space property is that the solutions apart from the the actual solution are not sparse. So how it is enforcing they are not sparse? It is in a way tying up with a condition that all the null space vectors that we are going to get, or all the vectors in the null space are not sparse. Essentially, this property is telling us all the vectors in the null space are not sparse. So if they are not sparse, so if you want to reconstruct, if you want to find another solution, we have to add a null space vector into the actual solution. So if that vector is not sparse, if this null space vector is not sparse, so we cannot get a sparse solution, because addition of a non-sparse vector with a sparse vector can never give us a sparse vector. Okay, so this is the intuition I have told you, but we'll go into further details how this works. Okay. So null space property of order S, let's go by its definition. What it says. So any null space vector U, if you have a matrix A, a sensing matrix or measurement matrix, so all the null space vector U you take, they admit to a property that you take any S entries of that vector. So any S is a subset of indices, S indices. S, the capital S is a set here which carries S number of entries, S number of values from this particular vector. And if you take any S subset, if you take its L1 norm, you create a sub vector out of this U. Okay, this is two sub vectors. It is created US, and the rest is the complement. If you create the sub vector, the L1 norm of this S, this sub vector, is smaller than the rest of it. Okay. So this is the null space property that is going to ensure that our measurements are unique in L1 reconstruction. Okay. So in other words, this tells us that our null space solution or null space vectors are all dense. So this is the condition. This is the null space property. Okay. So let's say we have X be a sparse solution. So now we'll see that how this null space property we can use to prove that as long as the matrix satisfying the null space property, they admit a unique solution. Okay. So in L1 minimization. So again, the same style of proof, we assume that another solution V exists. That means AX equal to AV. So now V is another solution, and I want to split this vector into two components. One is VS, that carrying the S sparse, the S coefficients exactly at the same indices of X. Okay, so because X is a sparse vector with support S. So S carrying those indices where the non-zero entries are present. So I have exactly taken, let's say, this example illustration. If you take, there are two positions where the X having the non-zero entry, and V is another solution that is admitting the same measurement. So I have taken exactly the same locations. Okay, same as this, and I have taken it out, call it as a different vector V subscript S, and the remaining part of it I called another vector V subscript S prime or S complement. So I splitted this vector into two components. Okay, you sum these two vectors, that is going to be V. So now I can rewrite X like this, adding the VS component into X and subtracting the VS. So if I add VS component, this is again the sparsity positions will not change and the sparsity will not change. This is a sparse vector, but the values will change. So this is X minus VS, and this VS that remains the same. Now, if I use the triangle inequality, so what I say that now I have split X into X minus VS plus VS. Now if I use triangle inequality, so basically U plus V norm is less than equal to U norm plus V norm. I'm writing it for simplicity with single bracket, but it's double side. So this is the triangle inequality that we're going to use. So if is the case, So this is basically upper bounded by the norm of sum of these two vectors. Okay, now what I know about these two vectors. X is a sparse vector. So if I split X exactly into the same indices set at S, I can write it as XS. There is no harm. And Vs as Vs. Vs is the another, I mean that the remaining part of V. Vs that we have already discussed. Okay. So since the support of X is S, okay, so this U is a null space vector that admits this because A times X is equal to A times V equal to Y. So let U equal to X minus V is actually a vector in the null space. Then what it says, if it is a null space vector, so I can take from this because X minus V is the vector in the null space, and what we are referring to here, X minus Vs. Basically, I took exactly the same indices of the subset of the set S from this null space vector U. So this can be replaced by US. Okay. So basically, the indices, the non-zero indices from the true solutions, I extract from the null space vector U that is coming out of X minus V, because X and V are both the solutions admitting to AX. I mean A times X and A times V equal to Y. Okay, and Vs remain as Vs, that is from the original the solution V. Okay, so this is fine so far. So now what I know about this null space vector, so I'm going to use the property that we have just discussed, that is the null space property. So what is the null space property? We said that any S subset of a null space vector is smaller than the complement, right? Complement set of these indices. So what we have earlier, we had this, and now it is a subset of the vector from the null space vector U. So now I can replace this with this one, USC complement, US complement, okay, because it's an upper bound. If you recall, we started with triangle inequality, we're upper bounding this norm of X. So this is basically, we can further, this inequality can still hold because of we can replace this with this null space property. Okay, so now I split this U into two parts, US and US complement. So I'm replacing this as US complement. Okay, here. So this got replaced. This got replaced with this. All right. So what is actually US complement? This basically is talking about X minus B's, the entries of X at the S complement and entries of V at the S complement. So if you subtract these two entries, what is the entries of X at S complement? We know X is a sparse vector and the indices are present in the set S. So S complement is nothing but 0. So if this is 0, so basically in essentially this is same as minus Vs. Okay. So minus Vs complement. So if I put this is minus Vs complement. Okay. I can replace this with this. It's because of the fact that X is a sparse vector we started with. So what it is telling, now if you look at this, minus of a vector, the norm doesn't change. So if you add the absolute norm of a vector and its complement, it's same as its own norm. Okay. So what is essentially telling us, it is essentially telling us that we started with this upper bound x1, we split it into two parts. So x1 is larger than sum of these two vectors, and we land in the situation where we prove that x1 is actually smaller than v1. So what is telling us that any such vector which is admitting this a times v equal to y is always going to have a larger L1 norm compared to the actual sparse sparse vector s x, provided we have this null space property. So this is the key. This null space property is the key to get this uniqueness. Okay, so L1 minimization recovers successfully now because a null space property is satisfied. So in fact, null space property is a necessary and sufficient condition for recovery of the L1 minimization. Here we have only proved the sufficient part because we started with null space property and showed that with null space property we can show that there is no other solution exists apart from x with a smaller norm. But we haven't shown the necessary part yet. So we'll leave it for the time being. And we'll move on to the condition because we have started the discussion with two properties, that is spark, and spark further strengthened or quantified through RIP. And now I'm going to tell that null space property. I have already discussed null space property, but now what should be that null space property? How we can ensure a null space property? Null space property can ensure by restricting the RIP constant. Okay, so if you restrict the RIP constant to be less than 1/3 in your sensing matrix design, then it can ensure a null space property exists, and that means our L1 minimization problem will work. Okay. So we have to go through this proof for this null space property. I think we have time. We'll continue. Probably I won't able to show some applications if you. So Dr. Nilkandan, so how much time do I have?
Maybe you can have 10 more minutes.
Okay, I will try to go through this quickly, the null space property, or otherwise we'll take a look into the solution. So some applications that we are interested in, so we are talking about. Okay, so let's, for the time being, let's forget about how this null space property is derived. But that is, if you put this condition on the RIP constant, we can easily show that the null space property can be achieved. Okay, so with this, let's move on. Let me go on to the. Okay, so now we have said that, okay, nice, L1 minimization is fine, L0 to L1 we can do, but what is the way to solve this L1 minimization? Of course, it is very easy to solve because we have landed into a scenario of a convex optimization. So we call such problem as basis pursuit. There exist many efficient techniques to solve such problems. For real valued problems, we can do linear programming to solve such minimization problem, and for complex valued problem we need a kind of second order cone programming, and also there exist many other toolboxes to solve such problem in MATLAB, in other kind of computational environment, and the computation is in polynomial time. It's no more combinatorial like for L0 norm. So in polynomial time we can solve this problem, and the beauty of this solution is that we don't require, though all these derivations and guarantee of uniqueness, we take some value of S to ensure the reconstruction guarantee. But in reconstruction, whether we are successful or not, that is depend on the basically the condition on the matrix. But as long as the unique condition is guaranteed, we need not know what is the sparsity. In fact, there is an upper bound on sparsity, but we can always reconstruct any S sparse or less than S sparse signal using this minimization without the knowledge of sparsity S. Okay, typically it performs best, but of course there are many solvers exist. The but part I will come later because it solves best, but though it's polynomial time, still people believe it's not a practical algorithm in many sense. Wherever you need real-time decoding or real-time applications, they have. That's why this all branches of greedy pursuit have developed, which are more efficient in terms of computation, and that gives a much quicker solution. that we will discuss soon. But another class of similar problem that arises from this L1 minimization is BPDN, where, as I said, the measurements are not exact, it's corrupt, you have this insignificant coefficients. Similarly, this lasso and dancing selector, all such problems align in the same direction. Now we move on to this greedy pursuit. As I said, this is very essential for practical purpose. In many of the practical applications, people choose to use a greedy pursuit over a basis pursuit, whereas basis pursuit has all such nice guarantees. Of course, greedy pursuit, I haven't shown any proof here, but there are some beautiful guarantees have been developed for this greedy pursuits as well. Right, so how does this orthogonal matching pursuit works? This is a greedy pursuit algorithm, a practical algorithm that gives a sparse solution, or in a way give us more closer to a L0 solution. It solves this problem. It assumes that each time it solves for a one sparse signal. So it takes the first measurement vector and find the best one sparse approximation. Okay, that means a sparse vector only carrying one value. And after finding that one sparse approximation, it updates the coefficient and retains the coefficient position. You look at this. This one sparse approximation can simplify it to be a matching filter, or can be simplified to a correlator. So you take the correlation of the measurement with the measurement matrix. You find the maximally correlated column. That gives us the coefficient, gives us the value, and the position gives us the index. Okay, so like this, you keep iterating. Okay, I'll not go into this detail. So each time you come up with a new measurement vector, the new comes from the residue. Okay, you take approximation on the first sparse vector, whatever remains as the error, you take it as a new vector and again search for the best L1, so a best one the sparsest solution with one sparse coefficient. Okay, again that matching procedure goes on. Okay, so like this it works, and that's how this residual, as I said, being updated in each iteration. To give you a pictorial illustration how it looked like, it's the original sparse signal and this is the measurement we have obtained, but how this iteration works is like this. In the first iteration, you take a, as I said, search for this one sparse solution, right? So only with one coefficient. So you just take the measurement y, then you correlate with the all possible, all the columns of measurement vector, and you take the maximum value. So that in a way tells you the first approximation or sparsest approximation that you're getting at the first iteration. You retain that and that position. The next iteration, so this is the residue. So after you get this approximation, you subtract the approximation from the original signal and you get the residue. At the residual signal, you again do the same procedure. You keep on matching and get the second best. This one we have written already, the second best signal, second best matching from the measurement matrix. And again, you keep on iterating like this. So that's how this OMP works. Okay, so let's look into some applications quickly. I started with imaging. So as a imaging person, I would like to show you some imaging example. Single pixel camera is a true sense compressive sensing application, you can say. How it works like this. We are imaging a scenario or any kind of scene with a CCD array. So what it basically does, the lens project an image into the position of a CCD array and you spatially sample all positions. That is point-wise sampling. But instead, if you use a compressive sensing, so we need kind of a aggregator or kind of a global sampling scenario. So here, this DMD act as this mask that basically get multiplied with this scene and then summed up. So it acts as this DMD is basically a deformable mirror that can create actually a kind of Bernoulli pattern. You can say that, okay, or Hadamard patterns for Hadamard matrix, and then you take this random basis, random rows. So that way you obtain these measurements, and these measurements can be transmitted wherever you want to transmit or you want to store in a computer. And from these measurements, we can really reconstruct back the signals or the image using they've seen the sparse reconstruction techniques or L1 norm minimization. So this is the true setup of an imaging setup where R is the object and the light source illuminates the object. Of course, sunlight or whatever the lighting source that illuminates the object, and it reflects back through the lens to this deformable mirror here, this DMD, and then this light comes back through this aggregator lens and to the photodetector. Photodetectors basically reads the voltage level for the amount of photon coming out of this seam, and this, of course, this mask getting multiplied. So this is the reconstruction of this. This is 255. This image we are trying to reconstruct R. You can see this R. So we have created this 6536 measurement because we have taken a square Hadamard matrix here, or a Bernoulli random matrix you can consider, where the measurement is 256 cross 256 dimension of a pixel of the image. So the dimension is basically here D is basically this 256 times 256. That number, this is the number, and the measurements are here for the first scenario. We have taken a square matrix, all possible measurements. Of course, because of the noise and all the reconstruction, because here we don't need a sparse solution because it's a square matrix and invertible matrix, so it admits direct a closed form solution. So this is the answer. But now we have taken the random rows. So random rows, only 11,000 measurements. That was 65,000, here 11,000. So in 11,000 measurement, the reconstruction is like this, and only 1,300 measurements, and this is the reconstruction. In a way, we have reduced actually the number of measurements that if you would have taken a standard camera for this 256 by 256 measurement, you would have actually taken this many samples, but we have only managed with this many samples. Of course, you can argue that it's a sequential acquisition where this is but this has a lot of advantage because here the resource, not only the number of measurements, the resource is utilized is minimal. Only 1 pixel of a camera is used to measure this signal. Whereas there we need this many sensors. But in many scenarios, many practical and signal processing scenarios, we don't have the luxury to have so many sensors. Okay? Because sensors are expensive. Similarly, I was about to tell you another example of compressed sensing is in channel coding. The sparse vector coding has taken interest by many researchers in the communication field, and it has been introduced in 2018 and so. So that's how it works. So bit streams are coded into sparse vector. Here in this example, a 5-stream bit has been coded to a vector. It's a length 8, a 9-length vector with 2 sparsity 2. So it is your sparse vector that you are constructing out of this bit stream, and then you are measuring. You are basically transmitting through your transmission channel, and also this is the sensing matrix that you have used here in case. Here, this is a Bernoulli random variable and random matrix, and that's how you transmit the symbols. And this is the error rate that is compared at different SNR for AWGN channel. And this is the sparse code vector, the CV, and it shows to be promising. Of course, this lower bound was derived for this sparse code. Theoretical lower bound, but then this is the true measurements that they have obtained for this SCV and PDCCH. I am not a communication guy. I don't know exactly what this PDCCH. I believe this is the current LTE technology that they use this kind of coding. And polar code is of course popular code. So that's all. And with this. So I summarized that we went through this compressed sensing, the foundational theoretical guarantee, and the intuition behind the compressed sensing, and we've seen the general framework and several variations possible in the time. And then there are many algorithms exist. So to conclude, the applications are from diverse fields. Just to show, I have just shown 2. You can also think of many intuitive applications where such objective functions come into play. Okay. All right, so thank you for your attention, and any question I would be happy to answer if I have time. Yeah.
Yeah, thanks, Dr. Sujit. Thank you very much. So I open to the participants. If you have any questions, raise your hand. You can interact with the speaker. Okay, so one of the participant asking, any good book on compressor sensing?
Well, there are so far. I must tell you that there is no good book, but there is a collection of good. It's a, how do you say that, book chapters by Yunana Ildar. You can read this Yunana Ildar's compressive sensing theory and application. But it's not a book, like it is not designed in a sequence like to bring into the field. But still, there is a good collection of material. You'll enjoy that since you have already seen the lecture, if you have already understood a bit from here, if you're new to the field, and then if you already know this field, then it is a good book. You can start it.
Yeah, just add to your point. If you have to look at the abstract concept in the compressor sensing, I think it might be difficult for you to find a single book which would cover you all the things. But if you want to know the applications of compressor sensing in wireless communications, there are plenty of good books. I can suggest later sometime. Any other questions? Okay, fine, Sujit. Thank you very much for your time. And almost we have taken 2 hours continuously without a break.
I'm really sorry for that. Yeah, thank you.
In fact, yeah, we thought 1.5 hours, but we have somehow managed 2 hours. Thank you very much for your support. So we will get in touch with you if some participants would like to review. Thanks. Okay, so maybe just 10 minutes break. All of you be here, or you can log out and log in. We will start at 11:10.